Now that we know about voltage and potential differences, we need to look into the actual channels and how you control this across your membrane. So first off, these plasma membranes are going to have different channels. The channels can be very selective. They might only allow one particular ion through, or they might not be very selective at all and allow anything to pass through. So depending on the channel, it can be very selective or not at all. It depends on what is necessary. We also have then what are called leakage channels. In the case of leakage channels, they're going to always be open, but they only allow for a very slow transfer of ions across. So you're looking at one here, one there. It's just meant to help rebalance things a little bit at the very end. So these leakage channels are very low flow of ions. So there's not a whole lot going through these at any one time. When you start looking at the leakage channels, you're going to notice that it's concentration based. You can see all the ions down here and only one ion up top. So it's going from the inside heading towards the outside. So leakage channels are working on the principle of diffusion. It's a passive process and it has to only work with diffusion and a concentration gradient. So this is going to help to kind of equilibrate the concentration sometimes. If given enough time, this would have a total equilibrium on both sides. Now, that's not going to happen because our bodies need to maintain the resting membrane potential, which means we maintain high concentrations of sodium and potassium in certain locations. But this is kind of there as a helping to make sure everything works appropriately. Another type are going to be gated channels. Now, gated channels are going to come in a couple of different, I'll call them flavors in essence, but a couple of different styles. They're going to open and close in response to particular signals. So if we're looking at gated channels, there's three main types we'll look at. We're going to see chemically gated, or known as ligand gated. We're going to have voltage gated and mechanically gated. So in the case of the chemically gated or the ligand gated channels, these ones will open if a particular neurotransmitter or a chemical is going to bind. So for example, we've already gone through the muscles and the neuromuscular junction. Remember in that case, the neuromuscular junction, acetylcholine was released from the neuron towards the muscle. When that acetylcholine bound on the motor end plate, that was a chemically gated channel. That acetylcholine binding triggered the opening of that gate. So chemically gated or ligand gated are going to need a physical chemical to bind in order to open. The second one, voltage rated. If it's voltage rated or voltage gated, that means you must have a membrane potential change to open up. So if you're at the resting membrane, maybe the one is set to be closed, then if that resting membrane doesn't stay at negative 70 millivolts and it starts going higher, and the membrane around it is negative 65, negative 60, negative 55, there'll be a certain point where it'll trigger and it'll just open up because the membrane voltage around it changed. It can work the other way around too. Maybe you're at positive 30, but that might be the trigger to open up a particular voltage regulated channel. So these voltage regulated channels or gates open based on a particular preset difference. So whenever the membrane around it reaches a certain voltage, that's when they react by opening. And the third one is the mechanically gated. For this one, there has to end up being a physical distortion of the cell membrane. So when the cell membrane shifts or moves or something happens to it, that can allow for the mechanically gated to open up. So three different types: chemically or ligand gated, voltage gated, and mechanically gated. So let's look at the chemically gated to start with. I already mentioned that you need a physical chemical to bind. So on the closed side over here, you'll notice acetylcholine is not bound yet. It's there, it's getting closer, but it's not bound. That means the gate is closed. Nothing's passing through. But to the right now, once the acetylcholine binds, you can see it's into the actual channel. That binding has triggered the channel to open, and now you have the ions flowing down their concentration gradients. Again, diffusion, but that's going down their concentration gradients. So it has to have a physical, actual chemical bound. Voltage-gated channels. In the case of voltage-gated, if you notice, if the voltage is, in this case, negative 70 millivolts, it's resting membrane potential. That channel is closed. So this gate does not get triggered at rest. Instead, if you notice, we've gone up to negative 50 millivolts. So this gate, it looks like, was triggered by reaching threshold, negative 55 millivolts. Because negative 50, we're past that, the channel is opened. So that means this membrane around it, all that membrane around it, that changed its actual potential difference. It depolarized from negative 70 up to negative 50, allowing it to pass the set point for this channel. So the channel reached a point, opened up because the membrane potential changed enough. That's a voltage-gated channel. And then the mechanically gated channel. The one on the left, if you notice, has the mechanical gate is closed. Nothing's passing through. But on the right, if you notice, the actual membrane changed a little bit and it popped that open. It kind of almost pushed it so it popped open. There was a physical distortion of the membrane. That then allows the ions to pass through. And just like the previous two, it's all based on diffusion. High to low concentration gradient. You can see on the side here how potassium is all heading out, leaving. It's going down its concentration gradient. Where if you notice on the other side, sodium over here is now coming into, because it's going down its concentration gradient. So it's all based on looking at that channel opening up, diffusion flowing through. So these gated channels, as you can see, they're all going along the chemical gradient, and then also can be along the electrical gradients. So you hold on, how does that both work? Well, if you're looking at the sodium ion, and we're talking about the sodium ion going into the actual axon, it'll go into the axon, and it flows from a high concentration to a low concentration. So that's going down its chemical gradients. But now once it's inside, you have all these positive ions grouped together. Does positive want to be with positive? No, they want to repel. Opposites attract. That positive wants to move forward to the negative environment ahead of it, where the channel hasn't opened up yet. So that's where you get this chemical gradient and electrical gradient, because both the concentration gradient, high to low, and the electrical gradient, positive attracted to the negative over there, that's the electrochemical gradient. That's what moves the sodium ion down the axon, or for that matter, down the muscle fiber too. So the electrochemical gradient. And this is what really creates our electrical currents, or why it's said to be an electrical current moving down. It's the ion moving. And as those ions move, they cause the next voltage channel to open because they change the inside voltage. All these positive ions moving cause that negative environment to not be as negative anymore. So the electrochemical gradient again, high concentration to low, positive is attracted to negative where you haven't opened the channels yet. So that's a little about the different channels, the gates, and how they're working. We still need to get a little more into the physiology of how the whole process comes together though.